Yeah, so let's get started. So it is our great pleasure to have Professor Nick McKeown here today for the Gerald Masson Distinguished Lecture Series. Nick is one of the legends in computer networking. He pioneered many fundamental networking technologies that are the key for the internet to run reliably, efficiently, and at scale. He has made many groundbreaking contributions to all aspects of networking, from his early work on efficient packet scheduling algorithms and router buffer sizing to his recent work on software-defined networking and programmable networks. In particular, Nick has greatly influenced my own research career by his seminal work on software-defined networking and programmable networks. Nick is not only an exceptional scientist, but also a successful serial entrepreneur. He has founded several networking startups, including Nicira and Barefoot Networks, that significantly changed the industry on how we design, build, and manage computer networks in practice. With all that, let's welcome Nick for his talk about the future of networking. Yeah, welcome, Nick.
Thank you so much. Can you hear me okay?
Yes.
Okay, good. So I'm going to be talking about today about the network as a programmable platform. But before I start, I wanted to say how delighted and I'm just super happy to be here. Clearly, it's, you know, most of us are reading about Johns Hopkins University at the moment because of the coronavirus and all the tracking and data that's being kept, and so it's just a real privilege and an honor to be here today. I'm going to be giving a talk which is the work of many people, and myself and Nate Foster at Cornell, Jen Rexford at Princeton, and 3 people at the Open Networking Foundation: Guru Parulkar, who some of you know, Larry Peterson, who probably many of you know, and Oz Sonay. And there's a Pronto team. You'll understand what I mean by Pronto a little bit later. So I'm going to try and let's see whether this works here. Can you see me okay on a set of slides?
Yes, very good.
Okay, good, wonderful. So I'm going to take a shot today at telling you why it is that I think that the sort of the network as a programmable platform is a really fertile new ground for networking research. In fact, I'm going to take a shot at telling you why I think it is that networks are going to change and improve a lot over the next 10 years, and how I think that's going to happen. But let me start with a story that we all know quite well. The way that we build networks, whether it's the public internet, enterprise networks, or the networks inside data centers, they've all changed a huge amount over the past 10 or 15 years, much more than it did in the 10 or 15 years before that. So today I'm going to focus on 3 big changes that I think are going to happen. The first is a change of control, a change of who is in control. So if we go back about 15 years, networks and networking equipment was closed and proprietary, built out of essentially mainframe computers, network mainframe computers that were closed and proprietary, often built and based on more than 100 million lines of source code. And this closed and proprietary nature meant that they weren't engineered that well, and they were bloated and power hungry internally. There was really very little incentive for the network equipment vendors to improve the quality of these products. And so as a consequence, we would refer to as internet ossification. And many of you may remember this from the mid-2000s, people were referring to the internet having ossified. Essentially, networks were hard to manage, they were unreliable, they were hard to secure and pretty hard to scale. And so when the data center companies came along, this wasn't going to be good enough for them. And instead, they started to build their networking equipment from white box switches, and they would control it from a server sitting remotely, running some control plane software. What they would essentially do is build homegrown switches with mostly homegrown software by buying merchant switching silicon and then adding to it some Linux-based switch operating system on top. One of the key elements of this was that it was open source, and this was kind of a new direction for networking, but I'll come back to that in a moment. As a consequence of building this homegrown approach, they found that the networks were easier to fix. They could add new features that they'd wanted for a long, long time, such as traffic engineering, to get more efficient usage out of their network. They could get faster recovery mechanisms, so it would be essentially up more of the time. And it would help them have local intrusion detection mechanisms because they understood how to do this best. And most importantly, it would lead to faster innovation within their networks because they could add stuff that they could do that they wanted to do for themselves. But I want to point out here that it isn't just that things like SDN, software-defined networking, OpenFlow, and disaggregation. This was a technique that they used, but the thing that really made it possible was their armies of extremely qualified software engineers that gave them the confidence and the ability to actually build this for themselves. I refer to this as a kind of a phase one of a big change that is happening in networking. And that is that network owners are taking control of the software that defines how their networks behave. Now, I wouldn't be telling you about a phase one unless I thought that there was a phase two, of course. And this is beginning to happen now. It's less well known, but it's been ongoing for the last few years. And Shin has been very involved in this. And that is that network owners are starting to take control of the packet processing that defines the behavior in their networks. What's happening is that fixed function switches and NICs are being steadily replaced by programmable switches and smart NICs that are able to, that we can program for ourselves using a language like P4 and tell it what to do rather than it telling us based on features that it had implemented. So the basic idea behind it is that if you're not in charge of how the packets are processed in your network, then you're not really in charge of the network, because after all the network really does is take packets from one place to another and then look at some bits and twiddle them as they go by. So let's step back a little bit and see how this came about. So, up until recently, networks were built with switches with fixed function pipelines. Fixed function pipelines were used because it allows for a very fast design. So these are ASICs that look a little bit like this. The red lines on the left and the right-hand side are where the packets enter and leave, usually over Ethernet. They go through a parser that will tell us where to find the various headers. And then those headers are processed by specialized processing stages in this pipeline. It's pipelined to allow multiple packets to be processed at the same time. So for example, here we might expect 4 or 5 packets to be processed at the same time, according to fixed function standardized protocols that we all are very familiar with. But to see where this is limiting, it helps to look at the insides of a switch. So typically the inside of a switch, it has a switch operating system that is controlling a switch ASIC shown here. And that switch OS is usually hosting a number of protocols, routing protocols, for example, like OSPF, BGP. There's usually about somewhere between 50 and 150 of these different mechanisms that are being hosted on the switch operating system. Now imagine that that you're building such a device. You write the software, usually as user space software, on top of the switch operating system, and then it controls how entries are placed into the tables of the pipeline that I showed you earlier, such that packets can be processed. But now imagine that you want to add something new. So a good example of this would have been in about 2010, when Cisco and VMware got together and they defined a new standard called VXLAN. You don't even know about the details. It's not particularly interesting. It's just a way of tagging packets to indicate which client they belong to in a large virtualized data center. Now, writing the software for this new feature meant just simply pushing some entries into a table and checking that they were there. The software probably took a few weeks to write. But because this was the most profitable, the most highly invested in area of networking at the time, by far, the build out of big cloud data centers, all the switch chip vendors were working as hard as they could to add this new capability into their switches, which meant adding a new pipeline stage so that you could process that orange VXLAN header as it went by. Now, the bad news is that despite it being very urgent, it actually took them 4 years to put this into the silicon. And this is essentially the essence of the problem. By the time that new feature came along, most people weren't interested anymore, or they'd found a way around it by hacking some other software or hardware together. And so you end up with these networks that are very kind of kludgy as a consequence. So what's going on here? I think of it as a little bit of a sort of a time of sort of a trend that's happening. One could argue even a little bit of jealousy that's going on amongst the networking community. So, and it's really this trend towards domain-specific processors that many of you will be very familiar with already. Now, what I'm showing you here is not a domain-specific processor. It's a general-purpose processor. But how do we use it? We write in a high-level language. We use a compiler, and we compile down to run on that device. And over the last sort of 2 or 3 decades, we've seen many of these devices. The GPU, for example, you write in a high-level language that gets compiled down to run on a device which has a specialized instruction set and a model of parallelism that's well suited to the problem. We saw the same thing in DSPs, digital signal processors, write in a high-level language, you compile down to run on that device, machine learning more recently. But in networking, this has never really happened. There were devices that were referred to as NPUs, as network processors, but they weren't really domain-specific processors. They were just a bunch of RISC processors sprinkled onto an ASIC. They weren't really optimized for the problem. So over the last about 10 years, starting in about 2010, I teamed up with a group of people at TI, initially in a project between TI and Stanford, to see whether we could define what came later to be called PISA, the Protocol Independent Switch Architecture, essentially a domain-specific processor optimized for processing packet headers. And then a little bit later, we started developing a language called P4 for programming this kind of device. So let me tell you a little bit about what the PISA architecture is. So first of all, it has a programmable parser rather than a fixed parser so that it can process packets that we tell it how to process, where to find the headers, how to break them apart. And this is followed by a number of identical stages, which are initially unprogrammed, and then we're going to program them using this P4 language. Each of the stages is identical. I show 4 here. That's only because that's all I could fit on the slide. In practice, you would expect somewhere between 12 and say 25 of these stages, depending on the particular design. But each of these stages consists of multiple memories for doing matches, and then multiple ALUs for doing actions. And there may be something like 100 to maybe even 400 of these memories and ALUs in one of these stages. I'll show you how packets pass through this in a moment. But one thing to notice is there's kind of 2 dimensions of parallelism that are going on. One is the pipelining. So each stage of the pipeline will be processing multiple packets at the same time. And then within a stage, there'll be multiple memories processing different fields corresponding to things that can be done in parallel at that stage. I'll show you how this works in a moment. By the way, on the screen that I have here, which is unfortunately a little smaller than I'm used to, I can't actually see if any questions show up in the chat window, which is what I'm used to seeing when I'm teaching. So if there are some important questions, maybe Shin can interrupt me and bring them to my attention. I don't mean to rabbit on if people have questions. So in this pipeline here, imagine that there's a packet approaching from the left-hand side. Here is arriving, the different colored squares just represent different header fields in this packet. The programmable parser is going to be typing the header and then from an electrical point of view, sort of breaking it apart into its constituent fields. And each of these fields would be presented to a match memory corresponding to the match followed by the action that we want to be performed on it. And then after that initial stage, we've mapped that set of headers into a new set of headers, possibly more because of encapsulation, possibly change values like decrementing values or just replacing values. And then as we go down this pipeline, we will map as we go down in each stage. And the number of stages of processing depends on the serial the serial dependencies within the program that we've defined. And when we get to the far end, those headers will be reassembled back into a packet and then sent along its way. So you may be wondering how such a program gets written. It's not that exciting, actually. It has 3 or 4 constituent components. One, as you might imagine, to program the parser. That's essentially saying, what do the headers look like? How do you find one header from another? They usually have some field in there to give you a hint. Then there's the tables, which are where the match and the action. So you describe a type of match you're going to have, and then an action that you're going to perform. And then a control flow, which says what sequence of tables the packets go through, depending on what they find as they go. So this P4 program, it kind of looks a little bit like C, although it's a little bit more tightly defined than your typical C program. Now, the work was being done in the context of a conventional wisdom that was sort of common in 2010 that said that programmable switches run about 10 times slower, consume more power, and cost more than the fixed function switches. And so this is pretty sobering, and it's also slightly embarrassing because this quote came from me, and it was sort of popularized at around about this time and was sort of pretty widely assumed. The interesting thing is that I can demonstrate that this isn't actually true anymore. And I want to sort of try and explain why, with hindsight, this actually isn't that surprising that this was, that this isn't true. I'm going to do it by way of example. And this is a switch chip that I helped to develop. I don't mean to say that this is somehow the best or the only one. It's slightly transformational, but in a way, it's one of probably what many switches in the future will look like. There's no magic in the way that it's designed. It's a 6.5 terabit per second switch, which at the time that it was produced in 2016 was matching the state of the art. So 65 ports of 100 gigabits per second. Which, if you stop to think about it, is a pretty immense amount of processing. It's about equal to the peak bandwidth of all of the Netflix traffic being delivered into the internet was at that time in 2016. But this is for the insides of data centers where the switching capacity is expected to be immense. So the first thing is that we found that it had the same power, performance, and cost as the fixed function switches that were best in breed, built in the same 16 nanometer technology at the time. To be honest, this was actually kind of surprising to us too at the time. It was programmed using P4, and if you write a program and it fits within that pipeline, then it will always run at line rate because there is no looping, there's no program counter, it's a feed-forward machine. A little bit of skepticism would be in order as to whether this was actually the case. So at the risk of sounding like I'm trying to sell you a device, I'm not interested in doing that at all. But just really as an example of the programmable versus the fixed, I just want to sort of show you a comparison. One of the large equipment vendors was building switches, and in fact they still do, out of both the fixed function silicon and the programmable Tofino silicon, both at about 6.5 terabits per second. I think the product they sell is 64 ports of 100 gigs, so 6.4 terabits per second. So in terms of the processing rate, they're almost exactly the same. The programmable device is slightly higher, but this all depends a little bit on how you count. So these are the spec numbers that come from those devices. So they came from the public numbers from the equipment vendor. In terms of power, they're about the same. The programmable device is surprisingly slightly lower power. This was actually where the biggest surprise was for us. We were expecting it to be about 10% higher than this. And then from a latency point of view, because you may be thinking, gosh, you're doing more programmable processing, surely it takes longer. It was slightly lower latency as well. And there's a reason for this, and that is because they're both pipelines, they're both feed forward, and that the programmable device because it has a compiler associated with it, it can pack everything into the smallest number of stages for the particular program that's being run. The rest of the stages can be switched off and bypassed. And therefore, for most programs, it actually ends up doing less processing than a fixed function counterpart. So I hope with this, I've perhaps, if I've not persuaded you, I've at least introduced you to the notion of these two phases that have been happening. Phase one, network owners taking control of their software. And now more recently, we're in the process of seeing them take control of packet processing too. The third trend I want to tell you about, which in a sense is a bit of motherhood and apple pie, but it has a lot of consequences for networking, in my opinion, and that is the rise of open source networking software. So what's happened is over the last few years, open source has kind of re-emerged as a legitimate and trustworthy way to control networks. As you probably know, the sort of the sayings of the early days of the internet was that standards were made by rough consensus and running code. It was essentially open source at that time. But over the years, as equipment vendors started to build closed proprietary equipment, they essentially controlled how things were done in a way that prevented open source from having a place. The operating systems, all the protocols that were implemented, they were all implemented in a proprietary way. Well, things have actually changed back a little bit. And with the emergence of things like, and you don't need to know the specifics of these open source projects, Open vSwitch, Sonic from Microsoft Azure, FBOSS from Facebook, FRR, which is a routing protocol suite, ONOS from the Open Networking Foundation. I'll show you a bigger list in a moment. But there have been many of these that have emerged. And people have now found that they can build high quality networks that are doing the necessary but non-differentiating pieces of the network in open source software, which they can develop with others, including with their competitors. So network code that was once opaque and closed is becoming, I wouldn't say it has yet become, but is in the process of becoming transparent and open. Here are a few examples going back to 1994, where the first first versions of Linux were introduced. In around about 2000, merchant switch ASICs that have emerged of sufficient quality that you could start building your own networking equipment out of those chips and then adding software to it. And so starting at about 2008, Google and Amazon started to build their data centers with switch chips and then Linux, and then their own routing software that was running on top. And then over the next few years, many projects have come about. There's just a partial list here. I actually stopped maintaining this list in about 2018, just because I couldn't keep track of all the projects that were emerging. There are enough projects now that you need good governance, and so some governance organizations like the Open Networking Foundation, or ONF, the Linux Foundation, and TIP, which was initiated by Facebook to develop open source software to help service providers and mobile operators. So there's a lot of activity taking place in this domain right now. Okay, everything I've told you up until this point, I would say is kind of a, you could almost say a statement of the obvious. I've sort of merely told you about trends that are going on, and many of you may have heard many of these parts of the story before. And in fact, in what I'm going to do next, I'm going to take everything that I've said up until this point as a given, as a starting point. So given that I'm going to take those as a starting point, it might be a good place for me to stop briefly and see if there are any questions about some of the things I've said so far. Maybe Shin, if you could moderate if there are questions, that would be helpful.
Yes, so if you have questions, please raise your hand. Yeah, for the first part of the talk. Yeah.
Maybe I'll carry on.
Yes.
Yeah. Okay, no problem. So the thing that I want to do next is to ask the questions. So what happens next? So if, imagine for a moment that you believe everything I've said up until this point, or that it makes sense. So what does happen next? I want to tell you what I think is going to happen as a sort of a starting point. There's something there is something interesting about the fact that networks, for the first time, are potentially going to be programmable from end to end. What do I mean by that? Programmable by those who own and operate them in a way that is relatively easy and cost effective for them to do. So everything that I show here would be programmable, and using perhaps the P4 language or maybe some other that replaces it in the future, both in user space and kernel space at the end host. DPDK already exists as a relatively easy way to program end host behavior, but now XDP and eBPF are evolving in the kernel as a way to process packets as they go through the kernel. All of these can be...
Hi, Nick. There are some questions here. Hi,
Great,
Randall.
wonderful.
Yeah. Sorry, Nick. This is Randall Burns. I'm
Hey.
head here in computer science. I'm sorry to hijack your next section, but I was wondering about open source and networks versus open source and operating systems, because you made that analogy. And I think we've all become very comfortable with the idea that open source operating systems are this diverse ecosystem lots of people are looking at and inherit some security properties from that. Which is, there's a trade-off between you're creating more attack surfaces, you're allowing people to inspect code, and yet there's also more eyes. Do you believe that there's a big enough community in networking to make network operating systems and network code be as closely inspected and as secure, or do you think that networking is providing more access to code that can lead to more attacks that won't be well inspected?
I think this is a fantastic question, and very timely, given all of the debates about the provenance of proprietary code inside networking equipment, particularly the political fight that's going on between the US and China and relating to Huawei and then ZTE last year. I'll tell you my opinion, but I can't offer an awful lot of data yet to back this up. And so that's why I think it's not only a great question, but it's an open question. If this was a relatively small community sort of hobbyist effort, then I think we'd have big reason to be concerned. What's happened in the switch operating system inside data centers is that Microsoft Azure put together a team to develop a switch operating system with routing protocols and various other software that they needed and telemetry software that sat on top. And then they recruited a number of other cloud providers. So publicly, there's Alibaba and Tencent and a couple of others that have got on board. And so between them, there's a small army of developers. And then the equipment vendors in the US, whether they are, folks like Dell and Cisco and et cetera, and then the chip manufacturers, like Broadcom and Intel and others, have all assembled teams. And so at this point, it's probably in the order of a small number of 100 people that will be developing a code base like that. In the internet service provider space and the mobile operator space, the Open Networking Foundation has probably a few hundred max developers between their own developers and then the contributors that are adding code to that code base. So I think it'll all come down to, if you have a few hundred, is that enough to make sure that you catch either bugs or deliberate malicious code that's inserted? And I think we're actually probably going to find out over the next few years. It appears that Microsoft for one, Facebook for another, and AT&T have decided that they would trust it, but that doesn't mean that they're correct. That answer your question?
Thank you, spectacular.
Okay, yeah, great. And also we have another question from Yair.
Great.
Hi, Yair, do you want to ask directly?
Sure.
Yeah.
So Nick, I wonder if you can just give a quick example so people can get the notion of what those programs actually are.
Oh, okay. Yes, yeah, sorry, I'm probably being a bit of a network head by not elaborating a little bit. So, in the most common cases are the ones that we typically learn about when we're learning about networking, sort of, the ones I showed before, like OSPF, BGP, that kind of thing. the management software that manages the system, think of virtualization software, or things that do encapsulation and tunneling, things that maintain state like load balancers, gateways, firewalls, etc. So they tend to be functions that each one of them is somewhat self-contained and not particularly complicated, but a typical router might have, you know, a couple of dozen to maybe 100 of these types of process. On top of that are usually things that are more orchestration, where one is usually referred to as traffic engineering, where you're taking a number of different parts of the network and trying to manage it as a whole over a slow timescale. For example, to make sure that at times of the day or night, different parts of the network are being used efficiently. So as I say, none of them are breathtakingly complicated, but once added up, then, you know, I know of one example of a Cisco internet backbone router that had about 120 million lines of source code to implement all of those functions. Does that help?
Sure, thanks.
Okay, good.
Yeah, thank you, Nick. I think that's
Okay.
all the questions we have now. Yeah.
Okay, wonderful. So I was just saying that sort of, you know, for the first time, the switches and the NICs are in the process of becoming programmable. Now, the vSwitches were already programmable. They were very complicated to program, but over the last few years, people have developed front ends to those, for example, using P4 as a simpler way of expressing the behavior, so you don't need to sort of dig around in the kernel to develop those. DPDK has lifted some of this into user space. There's a P4 front end to DPDK that's in sort of prototype form. And then for the kernel, you can define the behavior that you want for fast processing through the kernel. Again, P4 generating eBPF code as an example. So now you can actually program the entire pipeline for the first time. This has to have some interesting consequences, particularly given that the control plane itself has become programmable top to bottom. So what I mean by this sort of big change that's taking place is, for the first time, the entire forwarding plane is programmable. Over the last few years, the control plane has been made, you know, in many cases, open source, and certainly within the hands of those who own and operate networks. So you kind of get this entire programmability throughout the network. So this leads me to want to make some predictions. We can see a little bit later whether I happen to be correct in these predictions, but so it's a dangerous business trying to make predictions, particularly about the future, as the saying goes. But the first one is perhaps an obvious consequence of what I was just saying. I believe that NICs, switches, and vSwitches, and in fact the entire end-host networking stack, will have been programmable by the owner and operator relatively easily for at least 5 years by the year 2030. And I think this means we will think of the network more as a programmable platform rather than this assembly of standard specified boxes that come from equipment vendors. Behavior, I think, will be described at the top. It will be automatically partitioned, compiled, and run across these elements from a top-down behavior. I think that it will mean that every cloud ISP will make their network work slightly differently, and it will be programmed and tailored locally based on their specific needs and problems that they need to solve. And in here lies both danger, because they will work differently and therefore they may not work very well. But in here lies innovation and opportunity, because they will try to improve in order to be able to compete with each other over the business that they're all going for. I think we'll no longer think in terms of protocols. This is somewhat scary for people that teach networking courses. Instead, we're going to think in terms of software. Functions and what we call protocols today will have all migrated up out of hardware and being defined in hardware into software throughout the internet. And so I think we will just think of it as a platform that we program, and we will have interoperability as a consequence of writing software that gets compiled to all of the elements. This will certainly change the way that we think about networking. Networking students, I think, will learn how to program a network top-down as a distributed computing platform. we'll be describing protocols in historic terms, I think. Routing and congestion control will be programs partitioned across the system by a compiler. So if I want congestion control to be implemented entirely at the end host, I can do that. If I want it to be implemented by the host and the NIC, or the host, the NIC, and the switch in order to get congestion information out of the network, it'll be up to me, and it just depends on how I write the program. And it might be that the partitioning of that behavior gets done by a compiler rather than by a human. Where I think this takes us that is particularly exciting is that we can start to borrow software engineering techniques that have been developed for the computer industry. I think the networking industry has long been somewhat jealous of the computing industry and all of the things that it can do that we can't do because of the rigid, fixed nature of the devices that constitute our networks. So things like formal verification, on-the-fly checking of correctness, code generation for the control and forwarding, all of these techniques can be borrowed, if they prove to be valuable, can be borrowed from the world of software engineering. One thing that I've noticed that many people who are building networks do is who are programming networks for the first time, they introduce sort of fine-grained per packet measurement to monitor the function of their network in order to understand its performance. And I'm going to be explaining that in a little bit more detail in a few minutes. I think that stream computation will be routinely accelerated by the network with the introduction of load balancer devices and many more that will be offloading functionality from CPUs into these fast network processing devices. And Shin has done a lot of the most important early work in this area, which has been great to see. But with the overall aspiration, I think, for anyone that operates a large network is they want it to be programmed by many, themselves and others, and operated by as few as possible. They don't want to spend money on operating their networks. They have way too many people operating their networks today. And so if they can use this to get rid of functions that they don't want and introduce more ways to observe and control their networks, then that's what I think that they will do. So if I look at this overall structure and then think about the how all of this will work, as a consequence of it being all defined in software, it means open source can be a big portion of it. So networks will, for the first time, I'm pretty sure, be programmable, end-to-end, specified top to bottom, defined entirely by software, creating the opportunity to verify that they're correct by construction, to measure and validate, and to correct bugs through closed loop control. And because of open source, we, the research community, get to take part. And this is what I mean as a fertile new ground for networking research. So instead of thinking that we're writing papers and simulating behaviors using simulators, I think that we'll be able to actually develop and deploy in much more realistic production environments. And by the way, I think that this is going to happen in 5G as well, because yes, 5G required a lot of radio technology to be developed, but there's a lot of systems aspects to it that are going to change as well. And a lot of the ideas have been borrowed from the software-defined networking community to allow it to be defined in software as well. So this is going to be an important opportunity as well. And I'm hoping that it will be a bringing together of the sort of the wireline and the wireless portions of the networking communities. So let me spend a few minutes now give a view of how I think this will happen. The first is, as I said before, as people have kind of got their hands on more programmable elements for their network, one of the things that we've noticed that they do is they want to instrument more of it. They want to see more of what's going on. And that's because networking has traditionally been very, very rudimentary in what it allows you to see. You probably all familiar with ping and traceroute, but you may be shocked to know that virtually every production network in the world today is run using only those tools, ping and traceroute. They are the same tools that were used when I was a student many, many years ago. The world has not improved much beyond that. So, so it's kind of shocking and kind of scary that that's the case. But one of the things that I've noticed is that now people can program the network, they actually want to introduce a little bit more visibility. So how do they do that? Well, imagine that you've got a network like this one that I'm showing here, with a bunch of servers interconnected, and that there's some traffic or flow of packets going between two servers. It's kind of natural to want to ask of those packets to sort of examine one of them and say, how did this packet get here? Which path did my packet take? And it's kind of surprising that you can't ask this of a packet without sending a probe packet like a trace route today. What if I could actually go into that packet and ask it which which switches it visited along the way, and it could tell me I visited these switches at this particular time. Notice that every switch knows this information. It knows which packets went through and what time it was and the ID of itself as that packet went through. So this is information that it could tell the packet if we gave it a means to do so. In addition to knowing how a packet reached a particular point, I presumably want to know why it reached that point as well, in case there was a problem. So for example, every switch knows the rules that the packet matched on. So if the switch knows and a packet goes through the switch, then the packet could pick up that information too. And I might actually want to be able to say something like, in one particular switch, I followed a particular set of rules such that afterwards I could go and look for bugs and look for the errors in case I found a packet in the wrong place. So that tells me about the functional correctness. And I can tell you that until recently, there wasn't a single production network in the world that could answer either of these two questions. You might ask yourself, how on earth does someone run a network with hundreds of thousands or millions of servers without knowing this basic information? It's kind of humbling, actually, to think that anyone could manage to do that. So in addition to knowing the functional correctness, it's also natural to want to know about the performance. So for example, a natural one would be, how long did my packet queue at each switch along the path? Again, the packet could carry with it information about the particular delay that it experienced in each of the packets. And you can see here in this particular example that that red value indicates a problem. I probably don't want a delay of that value. So why can't I go to the switch and ask for the time series around about this time, showing me the queue occupancy, and the queue occupancy is the source of the congestion and the delay in a switch. If I can do this, then the next thing I might want to know is who caused that delay. I don't know whether it was my flow or somebody else. So who did my packets share the queue with during this time of congestion? If I know this information and can see here that my little green flow at the bottom didn't actually contribute much to the queue, there was some orange flow out there that was aggressively pushing packets into that queue. If I know that information, I can go back, I can throttle it, or I at least know whose throat to choke and whose software to go and modify. So it seems natural that we'd like the network to answer these questions, these 4 questions. How did my packet get here? Why did it get here? How long did it queue at each switch? And who else did it share the queues with? And until recently, this wasn't really possible, but something called in-band network telemetry is now being used to answer these questions pretty much for the first time at line rate. Now, it's a fairly expensive operation, but it is now practical to do. So let me tell you a little bit about how this works. When packets are going through the network, they encounter the switches, and those switches are merely going to tag the switches with metadata that the switches already have. Its ID, the arrival time of the packet, the queuing delay experienced by the packet, the rules that it matched on. And these will accumulate as the packet goes through the network. Now, the packet usually carries with it a little bit of configuration to say which of these it's interested in so that you don't overload the packet with too much information. When it gets to the last switch, a typical way to handle this is that information is ripped out and then sent to some collector, and the original unmodified packet is sent along to the destination. Now that collector can then analyze it and look at what's going on. This is a screenshot taken from a particular collector that was gathering this information. There are a few of these that have been developed by people who are building big cloud networks. So the time, the x-axis here is time, indicating the time of specific events of arrival of packets. In this particular case here, each vertical line corresponds to 1 nanosecond. So at each nanosecond resolution, remember that a switch could be processing 5 or maybe even 10 billion packets per second. But at this kind of granularity, it's likely to be pretty much one vertical line per packet that enters or leaves the switch. The different colors represent different flows. And so we can see here the different flows that constitute the made up the switch at this time. So this gives us a lot of information, and it's merely derived from looking at those samples that I showed you earlier. Now, there's very few networks, mostly financial networks, that have this kind of information today. But over time, you can sort of expect that people will figure out how to gather this information, perhaps on demand as they need it, if there are congestion events, making sure that this information is available to them so that they can quickly debug this network. The next thing I want to talk about is verification, and that is if we're writing software, then we actually know the original intended behavior of the network. So now we can check the behavior of the network against it. It also gives us a means to ensure that the software and the compilers are all in line with and consistent with that behavior. I don't mean to imply this is easy or that it has been done yet. I just want to give you a sense of how we might go about this. And an example I want to give you to start with of how we might build a model of what we believe the network should be doing. So the particular tool that I want to give you sort of a quick whistle-stop tour of is something called header space analysis. There have been a few of these sort of modeling methods that have been proposed. This is just one that we developed a number of years ago, and so the one that I'm most familiar with. So imagine a simple network like this, connecting hosts A and B over a simple 4-router network. Now, what header space analysis is going to do is to try and build a geometric mapping function that tells me how packets are going to be processed by each of these devices through the network. So we're going to consider a packet shown here with up to L bits of header as being a point in a L-dimensional space. And so if we think of that point here, that red point here, what the switch is going to do is going to translate it on a different port to a different value of that header. And so as that packet goes through, that transfer function T1 of HP, H is the header of the packet and P is the port number of the switch. So they are combined in order to tell us how it's going to be mapped. If we then pass this through the network and take that mapping function at each of the switches in the forward direction as shown here, it tells me about what would happen if I sent any packet from A, from any point in the space, whether it would make it to B. We can then invert these functions and go backwards through the network to figure out what we could have sent in the first place such that it would end up at B. So these yellow cubes or hypercubes here represent the set of packets that you could send at A that would reach B, provably across the network. Now, this gives you a fairly powerful model that you can check against and verify things like, as a consequence, we could find all the packets that go from A that can reach B. It helps us define loops, regardless of the protocol or the layer. And it could even prove that 2 particular groups are isolated for security purposes. It runs quite fast. You can then map this onto a SAT solver or something like that. And we demonstrated a number of years ago that you could verify on the fly at least 10,000 rules being added to a network per second to check that they were consistent with this model. We also generated a automatic test packet generation tool that would allow you to identify a minimum set of test packets that you would need to send across the network in order to find out whether any of the rules were broken or misconfigured in a network. Now, it's no panacea, and I just PowerPoint animations tend to make these things look way too simple. In a practical point of view, you can't model stateful processing, and networks are having an increasing amount of stateful processing, particularly as they're becoming programmable. And so we need to figure out ways to extend this in an elegant way for stateful processing. And there are a number of people that have proposed ideas and a number of people that are working on it. Another way to think of it is in this model that is programmable end-to-end and top to bottom, I'm going to have this specified behavior at the top that I'm going to compile and partition and then eventually compile down into the individual into the individual devices, perhaps. If I combine that with my the way in which I'm controlling the network, it might give me some clues on how I can introduce a closed loop control to fix problems as I go. So for example, if I start at this point where I've not only specified, but as I go down through each step, used formal verification methods across the interfaces, the layers of abstraction as I go, when I get to the bottom, I can measure using my fine-grained per packet telemetry, and then potentially feed back to either throw an alarm or potentially one day fix that behavior, maybe not in the specification, but in somewhere in the state, somewhere in the way that packets are forwarded. And this would be the kind of a little bit of a holy grail, because it would allow the network to heal itself both for reliability and security purposes much faster. I don't want to make any claims that this is going to be here in the next 2 or 3 years, but I think that in the 10 to 15 year time frame, things like this should be quite possible. To this end, a group of us have started a project, been working as a team. As I mentioned before, Nate Foster from Cornell, myself, Guru Parulka from ONF, Larry Peterson, Jen Rexford from Princeton, and Oz Sanay from ONF. We started a project called Pronto, which is being funded by DARPA. And the idea is to build and deploy this network using software that has been developed by the Open Networking Foundation as a starting point, including 5G mobile control software. And then the green parts are the parts that we're, the green parts at the bottom of the side are the parts that we're in the process of trying to add as the kind of the research component of this, fine-grained measurement, and then verifiable closed-loop control. We're deploying this at ONF, Cornell, Princeton, and Stanford. If you'd like to learn more about what I've just been talking about, there are some good places to start. I'd highly recommend, if you haven't seen them, Larry Peterson's new micro books. There are online books that you can find here, one about SDN, one about 5G. They're very much from a kind of a systems approach thinking, and so they're not sort of steeped in the old protocols or in the wireless the wireless jargon that you often find when you go and look at cellular standards. You could consider deploying real systems on your campus or at home or at work. And what I mean by this is there are upcoming sort of 5G base stations. This is just one example. At the bottom right is one at Intel Labs. The one at top right is at ONF, that are being controlled by a open source software control plane that would allow you to do such a deployment. This is kind of in the early stages of deployment now. You could join, use, and contribute to the ONF EVA open source projects. They're kind of fun. And maybe extend it to add new applications and services. This is something that I would imagine a number of students will do over the next few years. Write and deploy new open source P4 applications and then make them available to others. This year at SIGCOMM, I would say about 25% of the papers used in some form programmable forwarding and the P4 language as part of the way of demonstrating some new idea. But there are many other open source projects as well, not just the ones that I've mentioned here. In SwitchOS is parts of the Linux kernel and other open source software projects to get behind. I think this is opening up and allowing us to try many new ideas, both in terms of in the lab, along our corridors, or even on a production deployment. With that, I'm going to stop. Thank you for your time, and super happy to take any questions that you might have.
Yeah, great. Let's thank Nick for this great talk. Yeah, and we have some questions.
Great.
Some time for QA, and yeah, and if you have questions, please raise your hand, and I will start with my own question. Okay, so yeah, so nowadays there is a very trendy term called data processing units, or DPUs, which is really a fancier name of smart NICs. And several companies such as NVIDIA and Pensando have released DPU products and position DPUs or smart NICs as a game changer. So I want to know that what is your thought on DPUs? Are DPUs going to fundamentally change the architecture of data centers, and what is the role of DPUs in the future?
Yeah, no, I think this is a great question. You know, we're currently sort of seeing a transition, which is sometimes a little hard to understand. I think from network interface cards, network interfaces that were sort of fixed and contained perhaps some proprietary mechanisms into ones that are sort of smart and programmable and push more of the processing out onto the NIC. This is a trend that's happening in almost all of the cloud service providers. Some of them, like Amazon, are going full bore ahead of building their own smart NICs where they put a lot of virtualization software and they put a lot of other accelerators. It's arguably where Lambdas and microservices will live, or in many cases already live, out on the NIC. And one of the reasons they're doing this is that the processing out there for the infrastructure is now taken away from the servers that they're leasing and renting to others. So in some ways, it's an accounting question of whether they want to offload the infrastructure software, which they think of all as a cost, away from those servers out onto the NICs. So that's sort of happening right now. You could argue that it's a bit of whack-a-mole because all you've done is move it from one place to another, and it may actually be less efficient than out on the NIC. But that does seem to be worthwhile in their minds for them to do that now.
I see.
As they do that, then it's a natural question to say, if I'm putting more processing capability out on the NIC, can that now become the interchange point between the CPU and various accelerators that form the sort of the compute cluster? I might have GPUs, I might have TPUs, I might have other devices, FPGAs, and this now is the sort of the brains that's determining where packets and information flow. So, there's a lot of people thinking that that might happen. It's a natural interface to storage and sort of intelligent storage as well. So I think it may happen. The term DPU seems to be being applied to it. I don't know whether it's the best term or not, but I think that there's going to be a lot of investment in that area for the next few years.
Okay, thank you very much. Okay, so next we have a question from Ben.
Thank you. So as a P4 novice, can you explain to what degree P4 programs are capable of looking into payloads? Like, for example, if P4 programs are capable of deep packet inspection or anything like that. And if that doesn't live where P4 lives, does it live? Where does it live?
Yeah, so that's a good question. So P4 was originally conceived of as a method for defining how packet headers would be processed. That was its original intent. And that was always seen as a kind of a starting point, because at that time, you didn't really know whether the physical pipeline would be capable of processing things inside the packet. As it turns out, when you're designing a pipeline, the typical way that the physical pipeline gets designed is, as soon as a packet arrives, it gets split, the header gets split from the data, and they take different paths through the device. So the header will go down a processing pipeline like the one I showed you earlier, and then the data would be put straight into a buffer. Now, imagine that you've designed such a pipeline, then you need to design that pipeline so that it can process the minimum size packet. Once you've designed it so it can process the minimum size packet, it means you have a certain packet rate. I referred earlier to 5 billion packets per second. That would correspond to the minimum size packet. So if you can process 5 billion headers per second, and now the packets are all twice as long, it means you've only got half as many headers arriving. So for the same processing capability, you could process the data as well, because the data is the same size of the header and it just goes down that pipeline. You've got the processing capability in order to do that. So there's no strong inherent reason why you couldn't process the data as well as the header in such a programmable device. It's just that today, most of the effort has gone into using it for processing the headers. My guess, therefore, is that over the next few years, you'll start to see devices that emerge that will be able to process the data through the same pipeline, and everything will just flow through that same pipeline. They're already capable of doing it, they just choose not to do it. It'll consume more power if you do it this way, so it'll have to be in instances where it's worth it. So for example, in deep packet inspection boxes, etc., so towards the edge of the network. The pipeline that I showed you earlier, in the specific instances that I've seen, it has a bus that goes down through all of those stages, which is somewhere between 4,000 and 6,000 bits wide. So it actually can carry a lot of the packet data anyway. And so the chances are that the things that you're looking for in many cases will actually be within that first 4,000 to 6,000 bits, but not guaranteed if you're doing some function over all of the bytes. So long story short, I'm sorry, I rambled a little bit, but that you should be able to do all of this in principle. Now the language, the P4 language, is specified in terms of you describe the structure of the data that you're looking for. So it doesn't have to be in the header. It doesn't know about headers. All it knows is about patterns to match on in the header. So if the data itself is more structured, you could in principle use the P4 language to do that. Mm-hmm. So I think it's kind of inevitable. It's just not been the first priority so far.
Got it. Thanks.
Okay, great. Next, we have a question from Ryan.
Hello. Yeah, I'm wondering with programmable switches and many users write the customer programs running on those switches. So is it going to be easier to introduce bugs and create challenges for the maintenance and the debugging compared to previously have some proprietary software written by a single vendor?
Yeah, this is the perennial question, right? And that is, I'm gonna give you a cynical answer to start with, which is I call it the IBM view of the 1980s, which is leave it to us, we're the professionals, we'll take care of it for you, and everything will work just fine. This was the mainframe story of the 1980s when they were trying to sell very expensive, complex applications that would run on top of those mainframes. And probably those applications like accounting packages and payroll and things like this, they probably were pretty reliable. I doubt that they were that much more reliable than many applications that have been written since. But the problem was there were probably only about 20 applications that ever got written because you needed to wait for them to write them. And they didn't really have that much of an incentive to create a long tail of applications for you. So in an environment where you allow other people to program, then at worst, they're going to produce a lot more software that is potentially less reliable. But the idea is that those who own and operate the networks will be involved looking, using, telling their friends which ones worked, running tests, fixing bugs at a much, much faster rate. What you're just describing now is essentially the same argument that got used against Linux in its early days. Surely it can't be as good as all of that code that's been written for Microsoft Windows. That seems kind of quaint and funny to say now, but it seemed very realistic as a concern at the time. And so I think that what we'll find is, yes, early days, there will be problems for sure. It's new software, there always is. But because it's open, because it will be using much more modern standardized conventions for coding practices, I think that over time, it'll become much, much higher quality, just as Linux has.
Great, thank you.
Okay, great. So next, we have the question from Yair.
Hey, so
hello.
Hey, so I was working for the last 2 decades actually on wide area network at the distributed system level. And so we programmed our network on that level on Linux boxes so that we can do things that the internet cannot provide, like marrying high reliability with high timeliness together, or to have multicast in the network. And as I was looking at the programmable network paradigm that you guys came up with, Shane is a good representative at Hopkins. What I missed there is, like, because I would like to offload things into those switches. Because the way we do it, we scale by having many, many servers, and we break flows so that each server only handles some of the flows. So overall, we can work at line speed for the price of servers, and then can do something very sophisticated in the programming because we do it on a server. So what do I miss in the switch to be able to offload to the switch? And what I came up with is I miss a little bit of storage per
You
flow.
use a lot of storage, actually. Yeah.
Well, no. I mean, yes, I know. I would love to have a lot of storage, but I know that's not possible. But instead of only, you know, a pass-through processing, can we have something that is a little bit of storage to have something like in between? Like, for example, if I want to do deduplication, can I have not the storage of the whole thing, but maybe like a dictionary storage, you know, just to help me with the deduplication, and then I can offload a lot of it.
Yeah. So my pictures and my sort of presentation and my view, I will be the first to admit, is very plumbing centric. It belittles the immense amount of software that I think that you naturally want to place at the edge. But I kind of take it as a given that that's, I don't mean well understood, but well recognized as an important place to do processing. And so, for example, there are, you know, if you, to give you a very specific example, actually, imagine that you're building a layer 4 load balancer for a network that is providing web load balancing or something like this. If the network is small and the amount of load balancing that you want to do is relatively small, you'd probably do best to do it in software. Not only does it give you more flexibility on what it can do, but the processing rate is probably fine, and you may be able to do it on 1 server, 2 servers, but a small number of servers. By the time it gets to the scale of a cloud service provider, we've seen cloud service providers today that devote 5% of all of their servers to load balancing incoming traffic across the remaining fleet. Right? By the time you get to that point, then you're talking about tens of thousands of servers that are being used just to load balance traffic across others. We've seen, for example, that a switch can potentially offload about 200 CPUs with a single switch. And, you know, the price is similar between the two. I don't know the details, but I can imagine it's similar order. And so you can see it becomes fairly appealing. However, the thing that you run up against is storage, because if you're trying to track consistent load balancing of flows such that if any, as the set of, you know, servers goes away, then, or changes, you want to be able to keep it or remap it to the set of working servers, then there will be a limit, and that limit will eventually be determined by the switch itself. And these switches are typically designed today to be able to have all of their state and their memory on chip, because going off chip is very expensive at the rates at which they're operating. So I think 2 things are going to happen. One is that slightly lower speed switches will be developed, which will have access to off-chip memory and off-chip resources in order to expand that storage, both for the kinds of things, you know, load balancing, but sort of key value stores and things like this. I think that's kind of inevitable. Right now, all of the effort is on the high end, because that's where, frankly, the most volume and the most money is. And so that's how you can kind of bootstrap the business. But I think there will become interest in doing that at slightly lower speeds too. I think the second thing that will happen is that as they become sort of cheap enough over time, then you can actually start to string several in series. In the applications that are state intensive, it's often the case that you're not that worried about the latency. You could take a few microseconds to go through several switches. Nice thing is it would have predictable behavior, and so you can actually do it by placing them in series. However, they're never going to replace, you know, a general purpose compute, of course, and so they always have to work in tandem somehow, you know, in tandem with it. They're offloading parts of the processing that are well suited to it. But we mustn't confuse that with offloading everything. That, you know, that isn't going to happen anytime.
Yeah, just enough to save a lot, right? So because I'm talking about flows here that the value of it, like if you look at, I don't know, $0.50 per megabit per second per month, on normal flows, these flows you can charge maybe 200 times that. And
Yes.
so if I can get a little bit of memory on the switch to support something like that, I can save a lot of processing on the server side.
Yes, that's right. That's right. And so it is a trade-off, right? Like any accelerator, you're trying to trade off what it is that it's worth placing onto it. And I'd say that we're nowhere near figuring out where the right balance is, right, at this moment. I would hazard a guess that for a lot of sort of 5G and cellular processing, where there's a lot of change and chaos in the way in which they're implemented, and not necessarily in the early days of deployment, very, very high data rates. A lot of that will be done in conventional CPUs. I mean, I think that's highly appropriate. As they become highly aggregated, or as you get to more dense microcells with base stations locally coordinating at very, very high rates, then you have to look at offloading it, because it'll be more power efficient and more cost efficient to put it into devices that are more like programmable forwarding planes. So I think it becomes just like another tool in our toolbox. It certainly isn't a panacea.
Okay, great. So do we have any other questions? Okay, so I guess, hey, yeah, do we have
you
more?
can at least give claps, right?
Yeah, so yeah, I guess that's all the questions we have. And let's thank Nick again, yeah.
Thank you.
Yeah.
Pleasure. It was a great pleasure. Thanks for all the questions. I've heard the talk before, so it makes it much more interesting when people ask questions. So I really, really appreciate it.
Hope we can have you to visit our campus next time.
Me too. Me too. Yeah, this totally sucks as it is, right? Yeah. All right. Take care.
Thank you.
Bye now.
Thank you.
Thank you.